So, in the previous lecture we started to look at the first order and second order conditions for minimality of a function, right? And okay, right at the end of the lecture, once everything was over, there were a few questions which not everyone was privy to, but it gives me the impression that a point or two needs a bit of clarification. First of all, there's a small little correction in order. So remember I had said this, right? Yeah, and I believe when I wrote this as a sufficient condition, somehow I probably wrote the semi-definite condition here, right? If you think about it a moment, I thank one of you who brought it to my attention that what I was doing here was this. Now once this condition is true, what you have on the right hand side is just the second order term, right? And the whole premise was that this term should predominate these fellows, right? Now of course this is, if this is semi-definite, then there's a chance that this fellow goes to 0 for certain directions. So that cannot be allowed to happen. So in fact this condition ought to be positive definiteness, okay? So that less greater than or equality condition, please get rid of that equality condition that I had mentioned the other day when I mentioned the sufficient conditions. The second order necessary conditions still remain the same, the semi-definite condition, but for sufficiency you need this to be greater. The second point, which again thanks to some of you who brought up this question, I realized perhaps we would do better to elucidate a little more. There was nothing wrong with what we said, but when I used this, when I invoked this Weierstrass's extremal value theorem, here's what it essentially meant. What was I invoking it on? Which is the function that is continuous? What is the argument of that function? What I was invoking that Weierstrass's extremal value was on this, as a function of, viewed as a function of V, alright. Once you look at this object as a function of V, then this is a continuous function in V, yes, and a continuous function of V evaluated over what? Over the unit ball. That's a compact set. Now, because this is a continuous function in V over a compact ball from which you are choosing these points V, the extremal value must occur by Weierstrass's extremal value theorem. Therefore, this must have a minimum, and that is where this condition becomes even more important, because that minimum is not 0. So, some number is a minimum of this fellow, some positive number. Why? Because it is positive definite after all. Yeah, so the positive minimum of this fellow is very important, because now you can keep making alpha smaller and smaller, make it smaller than the smallest value that is attained, so that the ratio of O alpha squared divided by alpha squared is smaller than the smallest value attained on that unit ball. And then along any possible direction, irrespective of what V you are choosing, it will definitely trump, this term will trump the higher order terms here, yes. So that was essentially the argument. I hope that that is clarified now. Some of you posed this question the other day, and I think it would be only fair if we clarified this point, okay. So that's where Weierstrass's extremal value theorem was being invoked, but in general it's a very useful result, okay, that a continuous function over a compact set will attain its extreme values on that set, okay, great. Now, so far we haven't really addressed the question of how to solve a constraint optimization problem. I mean, you might say, okay, you are still considering that set D an open set inside Rn, so that is a constraint set, but really the character of that D is not very vastly different from the character of the entirety of Rn. Rn is also an open set, yeah, you don't include the infinities along the different axis directions, so it's an open set, it does not contain all its limit points, yeah. However, if you think about it now, suppose a constraint set is given by something that looks like this, okay, again just bear with me, it's higher dimensional object, we shouldn't be able to even draw this by rights on the board, but somehow suppose it looks like this, and when I am drawing this boundary in bold, I am essentially saying that even the points on the boundary are included as part of the set. In other words, this is not an open set, okay. Now if you are somewhere over here, if this is your x star, all the construction that we have done so far does not forbid us anywhere from using those results that we have derived so far on this point, right. You would still say that, okay, grad of f evaluated at such an interior point x star should still vanish. Same argument, right, if you can go in this direction, you can go in its opposite direction as well, so it should vanish, right. If you have C2 function, then even the second order condition is back in business. But the moment you admit the possibility that such a closed set, okay, is also your constraint set, then you also have to account for points like so. Suppose this is another candidate point, yeah. Do you think that the derivation that we have carried out so far can be pushed through readily for a point such as this? If not, then where is essentially the difference going to arise from? Which part of our argument will seemingly break down if instead of this point we consider this point? Just go back to the steps that we have used in our argument. Which step was contingent upon this point x star being an interior point of the set or part of an open set essentially, because in an open set every point is an interior point, yes. Yeah, so this is now my D, a closed set, yes. Yeah, see, this is essentially the difference. Here there are certain directions along which if you were to traverse, you would still stay within the constraint set. But if you flip the direction, so if you flip the direction and were to traverse in this direction, why should I even care about what happens to the function along that direction? You are already going to violate the constraint. I am interested in optimizing or minimizing the function over the constraint set. You might attain smaller values outside the constraint set, those are none of my concern, right. So which part of our argument was dependent on using both V and minus V? Remember we had said that, look, if, what happened? If there was this, remember this G that we cooked up, and we said that alpha G prime 0, and we said alpha could be both positive and negative. So unless G prime 0 vanished identically, if you have a particular sign for positive alpha, you will have an opposite sign for negative alpha, yes, and that is why G prime 0 must vanish, correct. But now on points such as this, if this is your V and this is going to take you along alpha V, then along minus alpha V you are not even allowed to travel. So why should you then assume that this term which is multiplying alpha, that is G prime 0, must necessarily then vanish? Yeah, right. So move out from the domain of f to the G that we had defined and look at alpha G prime 0. The whole claim that G prime 0 is equal to 0 was predicated on the fact that alpha could be both positive and negative. But on points at the boundary such as this, alpha cannot be positive and negative both. Yeah, might be. I mean, for example, if you have something like this, and if you choose a direction such as this, then of course both positive and negative directions are admissible, but not for all directions, you see. Why is the all direction important? Because at the next step, when we said grad of f at x star is equal to 0, we said this is true for arbitrary v. So even if for certain directions, yeah, you might have both v and minus v admissible, at least grad of f has no good reason to identically vanish, because there are certain directions along which you cannot move. So along those directions, we really shouldn't care whether the function is going to decrease or increase. We are only interested in decreasing the function along all possible feasible directions of traversal. Yeah, let me write the term feasible. So then it begs the question, whatever we've done so far for this open set, should we then chuck it out of the window? Is everything useless then? Or can we somehow use some of those results to still arrive at some meaningful discussion in case the set includes its points on the boundary? Well, the answer lies here. So what is it? You should have, and I want you to be absolutely clear on why we are saying this, you should of course meet the condition is equal to what? 0. Why? What should this be? Greater than or equal to? What should it be? Reason out. What is it that you are interested in? If you move along any feasible direction, so V is one of those feasible directions, yeah? Because along infeasible directions, I really don't care what happens to F. Along feasible directions, what should happen? It should increase, right? Or at best, stay the same. So, can I write equal to there? What should be the condition? Greater than or equal to, exactly. That's what you would need along all possible feasible directions. So here's the sort of strategy, if I might enlist it as such. Suppose D is not an open set, suppose it contains points on the boundary. Suppose D also contains certain points at which F is not even differentiable. But let's say there are only a few in number, such points where you cannot differentiate. Then strategically, what should we be doing? Here's what we will do. First, list out all points where F is not differentiable. That's first set of points. Second, look at points on the boundary and only consider feasible directions of traversal at those points on the boundary, and list out all those candidate points which satisfy this. I'm not saying how easy or difficult this is, yeah, how computationally easy it is a different matter. I'm just saying strategically, in principle, this is what we should do. List out all points where you cannot use the grad, and therefore there's no other choice but to actually evaluate the function at those points and hope that those are only a few points. Next, if it's not an open set, look at the points on the boundary, yeah, and find out this quantity, check if this quantity is semi-definite, yeah, at best 0, yeah, along all possible feasible directions. I don't care about what happens along this, but at least along this direction, yeah, it should increase. Third, of course, among all interior points, equate grad f to 0. List out all of these points, evaluate the function at these points, and find out where you get the minimum, right? If you get one unique minimum, then you have a global unique minimum over the entire constraint set, okay. But such constraints are very tricky, yeah. Let's point out to you a fundamental flaw in whatever we have done here. See, at the heart of all this, I mean, when we think of things, we tend to think of things as very nice. And I'll just show you that the kind of strategy we have designed here rests heavily on perturbing this point or traversing from this point away along a straight line. Such traversals are very well suited to so-called convex sets. What's the property of a convex set? Very loosely speaking, if you have, so this is not a convex set, okay, this is not a convex set. A convex set is one where if you pick out any 2 points in the set, then the line joining those 2 points is going to be entirely contained inside the set. So traversing along straight lines is very well suited when you are living inside convex sets if your constraint set is actually convex, yeah. The moment you step out of these kind of nice kind of sets, sometimes to say that, oh, I am going to just traverse from x star along some straight line might not capture all possible feasible directions of traversal. Along some directions you might have to traverse along some curves which may be parameterized by some parameter, but not necessarily of this form that x star plus alpha v. Are you with me on this? Let's for example see something like this. So suppose your constraint set is, say this is x1, this is x2. So your constraint set is the entirety of the first quadrant, and let's say this line, okay, that looks really wiggly. Okay, I don't mind it being wiggly, I just want it to look a little nicer, okay. So points on this line, and so it's like a kite with a tail, yeah, it's like a kite, the first quadrant and this kind of a thing. So these are all points that satisfy the constraint, whatever be the constraint. I am not getting into an exact mathematical characterization of this constraint set, I am just saying it is some constraint set. But suppose your function f is something like this. Okay, where a is some positive real value, some positive real number, okay. What is so special about this particular choice? Nothing very special really, but so this is an example to illustrate what point exactly. Think about this point which is the origin. What are your feasible directions of traversal at the origin? Anything else? Can you traverse along a straight line and still stay in the constraint set anywhere but in the first quadrant? No, right? So if you are doing this check along feasible directions and you look at this origin here, if you are traveling along this, so take the, for example, grad f here, yeah, what's that going to be? 2x1 plus a, right? And the second one similarly will be 2x2 plus a, yeah. So if you are looking at it at the origin, what happens? So at 0, 0, this will be, and a is a positive number, right? So this is a vector pointing in the first quadrant. So its inner product with another vector pointing in the first quadrant will be what exactly? Positive, right? So you are, by traveling towards this direction, you are certainly going to be doing worse. I mean, of course, you can just take a quick look at this function, you can see that it's going to increase. This is just a technical way of seeing the same thing which you understand intuitively. Great, but here's where the deal breaks down sort of. If you go ever so slightly along this direction, in the third quadrant, along this curve rather than a straight line, this curve is something you hadn't accounted for in all your formulation because you were only concerned with feasible directions of traversal along straight lines. But if you traverse ever so slightly along this curve here, what happens? Take a point really close to this origin in the third quadrant and look at this function here. At the origin, this obviously evaluates to 0. But at a point ever so slightly away from the origin in the third quadrant, this one A still predominates this term. So A plus x1 is positive, A plus x2 is positive. So take this point so close that it is smaller, the magnitude is smaller than A. So A plus x1 is positive, A plus x2 is positive, but x1 is negative, x2 is negative, the resultant sum will be negative. So by taking a small little excursion along this curve on the third quadrant, you are actually going to be reducing the value of the function. But this could not have been accommodated within your framework because you were only listing out all possible feasible directions of traversal along straight lines. Yes? So these kind of constraint sets are incredibly difficult to deal with. There is no very clear-cut answer in optimization theory as to like satisfactory closed form solution, like you do this and you will definitely get a solution, right? These are tricky little beasts here, right? However, we will deal with somewhat simpler kind of constraints, and even there we shall see, or we shall at least be able to reason out that considering this straight line traversal is a bit too restrictive. Okay, what kind of constraints are we talking about? Well, constraints which we term as equality constraints. Before we get into equality constraints, let's just have a quick little discussion about what constraints look like. You think of the following: Ax is equal to 0. A is a matrix, x is a vector. Age-old problem from linear algebra. In the language of linear algebra, you are basically solving for the kernel of A. What is the constraint? No, don't give me straight line, just be a little more precise. What is the constraint here? Geometrically, suppose it's an n-tuple, x is an n-tuple. So A is an m cross n matrix. Let's say there are m constraints. What is one single constraint going to look like? Yes, a vector space. What sort of a vector space? If it's an n-dimensional Euclidean space, so x is an n-tuple, if I give you just one equation, if I had given you no equation, no constraint, it could be any point in n dimensions. The moment I give you one equation, yeah, the dimension reduces by 1, right, immediately. So if you are in 3D, I give you one equation, it means now you are no longer allowed to lie anywhere outside of a given plane. If I give you another equation, hopefully of another plane, which is not parallel to this fellow, not identical to this fellow, but intersects this fellow, what should that intersection be like? A line. So now you cut down your allowable region from the entirety of 3D to a plane, and subsequently one more constraint, you come down to a line. So equality constraints have this sort of an effect, is what I am trying to get at. But of course these are nice kind of equality constraints where they are linear. And again, in these kind of situations you might have feasible directions because these are after all planes, lines and what have you. Yes. But if on the other hand we were to try and accommodate a wider class of equality constraints, yeah. So let's say this region D, which is contained inside Rn, is specified by a bunch of equality constraints. Equality constraints of what kind? I say h1x is equal to 0, h2 of x is equal to 0 dot dot dot, hm of x is equal to 0. So these are my equality constraints. Yeah, if these were lines, if these were equations of hyperplanes, yeah, then each of them would be confining you to one n minus 1 dimensional subspace. If you invoke all of them together, and if all of those are kind of linearly independent constraints, what are your degrees of freedom now? You would be constrained to lie in an n minus m dimensional subspace, would you not? Yeah, this is actually the rank nullity theorem at work. Do you see that? Yeah, there are n variables, there are m equations, each of them being linearly independent means the number of degrees of freedom is given by the dimension of the kernel. So you can freely move around in an n minus m dimensional subspace. But again, I digress a bit because I am just getting into this kind of simple linear constraints. But let us say these are not linear equations, these are equations of curves. Now, do you think that there is any reason to suppose the kind of framework we have considered thus far, which is traversal along straight lines starting from the point x star, is going to be good enough to accommodate these kind of fellows? For all we know, let us try and draw 3-dimensional space. So, this is x1, x2, x3. For all we know, this could be your h1. Yeah, of course, I should give it the, yeah. The important geometric detail here is, if you squint your eyes and zoom in on a very small local version of this, perhaps it might still be made to appear like a 2-dimensional plane. But the overall picture is certainly nothing like a plane, right, or a hyperplane, right. Now you have another h2, let us say, okay, excuse my bad drawing here, but I guess you get the idea. So this now becomes your combined constraint, isn't it? The points where these two curves, these two manifolds, they intersect. It's like a line, but not exactly a line, it's a curve. Now, if you have to stay within this constraint set, it means you have to stay somewhere within this curve. So, in going from this to this point, if you're trying to use a straight line, that's not even a feasible form of travel. You have to reach this point to this point along this curve, because at every instant you have to keep meeting the constraints. It's no use if you're going from here to here along a straight line which is not part of the constraint set. So therefore, the kind of structure we have built with this x star plus alpha v is not going to cut it, okay. So next we shall see how we are going to try and address these kind of situations.